started. Okay, so today I want to talk about Dbux. It's a tool I've been working on, or rather we've been working on for now well over 2 years. And it's basically a debugger for JavaScript, a very, very different kind of debugger. We will get into the definition of debugging in just a second. But then we want to switch gears and basically look at how can we visualize and better understand and interact with the dynamic execution behavior of algorithms and data structures. So that's a little something we've been working on for now already 6 weeks. So I just want to show what we got so far, and that's gonna be the main 2 things: talking about debugging, and I'm talking about, or rather actually demoing a visualization and interaction method and tool for data structures and algorithms. And all of that is in JavaScript. Now, the first question you might have is why algorithms, JavaScript? That doesn't mix, but it just so happened that we were already working on debugging in JavaScript. So we just kind of went with JavaScript. Now, if this turns out to be good, then we can move on to languages that are more commonly used for algorithms, such as Python and so on. All right, anyway, so let's get started. General outline, how do we usually debug? What is a debugger? And then we're going to introduce debugs, and then we're going to introduce this tool that will help us visualize our algorithms, which is called a program dependency graph. Not a new idea at all, but we will get into that. All right. Number one, how do we usually debug? Okay, so think about this. So last time you ran into a bug. I mean, if you're programming on a regular basis, it probably was yesterday. Basically, any day you program, you will probably run into some bugs. Some of them are very difficult to find. We are talking today about debugging in terms of finding bugs. Solving bugs is an entirely different kind of mess. But oftentimes we have these bugs that are actually really easy to fix once we know where they are. It's this one line that was hiding in our code, easy to fix, but it's really hard to find. And that's what we want to focus on today. So what makes bugs difficult to find? Well, let's look at what debugging is and what a bug is, right? So the way that I'd like to look at it is a bug is a needle in a haystack. That's kind of what it is. It kind of feels like, I'm just realizing I think I've lost all my animations when I move. Okay, it's just something we have to live with. Sorry, I lost my, it's a little bit annoying, but it's okay. So we have a needle in a haystack. What does that mean? A bug is essentially one line of code that is faulty in many, 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 many lines of code. So maybe you have 100 lines of code, 2,000 lines of code, or 30,000 lines of code. At the end of the day, no matter how many lines of code you have, many of your bugs are going to be in one singular line of code. So finding that line of code out of these many, many, many lines of code, that's why that is what I would call a needle in a haystack problem. So what does that mean? Or maybe there's another way of looking at what really our programs are and what we could do in order to debug them. One way of looking at a program is to consider it as a factory. It's basically this really complex thing that does a lot of complex, well, things inside of it. And we just put some inputs in, and there's some outputs that are going to come out of that factory. That's kind of like how factories work. And that's also how our programs kind of work. And how do we debug them? Well, we sit on the outside looking in. We don't really know what's going on in our programs. You might think, well, we are looking at the source code and so on. But the source code is not the dynamic runtime behavior of our programs. The source code is a static description of that. So what is the source code? The source code is like a blueprint. So essentially, if you want to talk about, well, what is debugging really? Well, there's 3 things that we do in order to debug. Number one, we look at the source code. So what was that? That's basically a blueprint. It's like debugging technique number 1. We stare at the code one more time. And well, there's a lot of other things we do at the same time. We build up our mental models, we understand our code, and we think through it a few more times. And it's not just staring, but ultimately that's kind of what it boils down to. We look at the blueprint and we try to imagine what happens if our blueprint comes to life, and to then reason about our programs in that way. So that's like debugging technique number 1. Another very common debugging technique is, of course, to use our output. So we have the inputs, we have the outputs, we can look at both of them. But then as the program evolves and does all these things, we want to understand, okay, when does it what, and where does it what, and so on. I want to say why. Actually, the question that we have is why, but these techniques don't tell us really why. It's actually, they only give us much less than why. They only give us a little bit of the what and the when. And so the next technique to get the what and the when is our fax machine. So essentially a console log statement, a printf statement, that's essentially a fax machine that helps us to understand, okay, what is going on when, where. And then technique number 3 is, of course, the traditional debugger. Well, some people use it. I think there's a lot of studies that have shown many people don't use the traditional debugger. And the reason for that it is very limited in a utility. It's not actually a very good tool. And that is why we're talking today. That's good. Those are like the 3 main debugging techniques that are out there, I would argue. So there's, of course, other tools. Let's see. Okay. All right. So there's, of course, other tools, such as, for example, but those are generally more domain specific, such as your Chrome dev tools, right? Or your browser dev tools. Those are really, there's a lot of cool things there, like the networking monitor and so on. Those are definitely also part of your debugging toolbox, but they are more domain specific. They don't help you with general code. So that's why they are kind of like separate here. All right. So if we, again, look at our program and we consider it, let's say, a complex factory, then we kind of really don't know what most of it, like what is happening on the inside. And that's why I would like to call it like dark matter of debugging, because it's basically invisible and intangible. Like we can't touch it, we can't see it to us. That's why I like to call it the dark matter. I'm not sure if we are all that aware of the fact that a lot of the things that we would like to know, we don't know. And that is why we put a printf statement over there. And then we use the debugger, the traditional debugger, and get a little bit of information over there. It's not very effective tools. So at the end of the day, we have to rely on our brains. We have to basically establish these mental models and think about what could happen when and where and why, and do it again and again and again. And ultimately, hopefully, when the mental model is sufficiently complete, and when we have debugged our mental model, which are also always like faulty because our programs are so complicated. So oftentimes we actually have wrong assumptions about what's happening. So the mental model is actually buggy. So the bugs just propagate like that. And that's kind of like why it's very difficult to debug, I would argue. Okay, another little metaphor that I usually use, and that's also why you see the little flashlight and the looking glass here, or sorry, the magnifying glass here, is that the traditional debugger kind of works like, okay, I'm going into the factory, it's a ginormous factory, and I'm taking this magnifying glass and basically scan the floor for that little needle that like somewhere fell through the cracks. That's kind of like what the traditional debugger does. It works on a very low level, only in one place at a time. And you're also like bound kind of like by steps, and you can only step forward. So that's the traditional debugger is very, very limited in its functionality, and it's not a very powerful tool. It doesn't really help us understand many of the problems or questions that we have. All right. Well, this whole problem, it sounds like, you know, I might be saying this for the first, or you might be hearing this for the first time, but this is definitely not new. All the way in 1997, Henry Lieberman from MIT was very passionate about this. He wrote this article and was talking about how we are absolutely we are kind of like underestimating the cost of debugging, and how important it is for us to have better tools to help us to map this static description of our code to the dynamic actually execution behavior, and help us establish the mental models about this kind of about all the complexities that are happening in these systems that we are building. And that was in 1997. And in 1997, he already argues that basically for 30 years, nothing has changed. So that was 25 years ago. So that was 30 years, no change. Now another 25 years where basically little has changed. The tools we use are basically the same as back then in 1997. It's kind of funny that way. And so it's a total of basically 55 years that we haven't really gotten any sort of real innovation in this space. So in terms of, can we maybe better get better tools that kind of tell us more of the why in our programs and less of the when and what. All right. So another issue is, of course, then, why is this not improving? And that's a lack of debugging culture. We don't really talk about debugging, right? When do we ever talk about debugging? I'm not sure. Do you have a course on debugging in your university? If I can ask you, Jürgen. If I may, I'm not sure if you're there.
Yeah, we have no explicit course on debugging. No.
Yeah, that's
I only know Andreas Teller in Saarland who at some point had a course on debugging, but I think that's the only one I know.
Yeah. Zeller is a very, very big name in debugging. He is doing automated debugging. So what they are working on is debuggers that can automatically find your bugs. And that is a lot of research, and that's great and awesome. But essentially they are also, Zeller also has I think it was free course on debugging on Udacity from 2012. But that is mostly a course on how to build your own little debugger, if I remember correctly. But actually, don't cite me on that. That was like my first impression that I got from it. I didn't actually look at it in depth, but I scanned over it, and it looks like it tells you how to basically understand certain aspects of your program automatically. But it doesn't actually address like many of the concerns that I would have. I love Zeller's work; it's great, but sadly, it doesn't. Yeah, go ahead. Sorry.
It is, so one thing that I remember from that course, but it's been a while that I looked at it, is that he does talk about debugging as building hypotheses, what I think you called mental model, right? And approaching it from a more scientific perspective rather than just poking with printfs, which goes into his philosophy of even back in the 90s where he introduced delta debugging, right? So I think he continues in that regard, but I think you're actually right that he goes on to sort of promote the research of automated debuggers.
Yeah, that's right. Definitely an important field of study. So in 10 years, we don't, who knows, maybe, or like 100 years, we don't even have to use our brains anymore for that. We have an AI for that, but well, short of that, as a developer, I don't think we can sufficiently rely on these tools. And there's a lot of studies on that as well. They can be really great in some scenarios, and of course, in most scenarios they will falter and kind of like send you on a wild goose chase because the information they give you, sadly, not to the point. It tells you, oh, it's probably over there, and kind of like helps you maneuver in that direction, but it's actually all the way over there. But yeah, there's certainly issues with automatic debugging as well. But yeah, so in general, we just lack this culture. We don't even have courses on debugging, and even if we had them, well, what would be a good course and all that in our companies as well? We do spend so much time and energy on debugging, but we do barely talk about, if ever, about debugging strategy or debuggability. We talk about testing and testability, but well, debugging is a different kind of thing. As yet another layer to that. And how much do we talk about, well, dynamic analysis, which is the underlying, well, core fundamental field, basically skill and strategy to approach any sort of debugging. It's the basic dynamic analysis, understanding the execution, the dynamic behavior of the program that has just executed or that is executing. And then how much time do beginners spend on learning to debug, right? Again, there's no courses on that, or very few. And then how much time do professionals spend on improving debugging skills? And again, it's not even any talk about that in most scenarios. So there's a lack of culture on top of all of that. And so there's little demand for improving those tools. And where there's little demand, there's not the money, there's not the funding in order to get you to the point where we can actually get those better tools. All right, so next up, what is a debugger? So let's quickly define that. So there's all types of debuggers, and then there's these interactive debuggers. And of that, then there's the debugger. So the debugger, whenever you talk about the debugger, it's actually just one specific instance of an interactive debugger. I call it the traditional debugger to better differentiate it from the work that I'm doing, of course. But mostly, in most cases, you will just use the word the debugger. Of course, what is the debugger? Let's look at that in a second. So in general, we've just talked about the automatic debuggers. We have the semi-automatic debuggers, and we have those interactive debuggers. So semi-automatic debuggers are basically just like automatic debuggers, but where you can give some feedback to the AI. And then hopefully it will make better decisions, or it will eradicate a false positive more like earlier on. So semi-automatic debuggers are certainly more interesting than automatic debuggers, but still, I believe, interactive debuggers is just of course, where I am right now. This is just absolutely the most fascinating thing to me on a personal level. But yeah, the debugger is just one. Okay, this is the most important thing when you talk about the debugger. It is certainly not all debuggers, but sadly, it's the main implementation of a debugger, and also there's really not any other implementation out there on an industry level and like mainstream level. There's very, very little other than the debugger. So the debugger, what is the debugger? It's BVCF. So that's breakpoints, value inspection, call stack, and forward stepping. That's a little bit limiting. There's other things that they usually have, like watch lists and whatnot. But other than that, like the most core set of all these types of debuggers, which are all called the debugger, are basically that: breakpoints, value inspection, call stack, and forward stepping. Maybe you can do better than that. So what is a good interactive debugger? So a good interactive debugger, if it's a needle in a haystack, it's of course anything that interacts with metal, such as a metal detector or a magnet. So that would be great for interactive debugger. That's more or less like like this would be great to have. But sadly, we kind of like currently still going with that magnifying glass. So what else can we do? So what I think we want to do is that we have this dark matter of debugging, and what we really need to do in order to improve this whole situation is to make it maybe a little bit more visual and interactive. That's it. That's really the main thing that I think needs to be happening. And how would that work? So here I would propose a basic model of general interactive debugging, and that is this. So we have the source code, and we have a system, and then we run that source code on the system. We load it into one or multiple processes in terms of an application. So we are running the application now. And next, we have a debugger. So the debugger usually has a backend and the front end. The backend then takes in, it has a control module, and the control module can be used to control the application. Like, for example, in the traditional debugger, you can pause it, and then you can set those breakpoints, and you can interact and kind of control the application a little bit. Not every interactive debugger has a control module. And then we collect some data from the application and or the system. The system also, I use the term loosely, so it could be everything, the interpreter, everything that's basically below your language level. So for example, in terms of Node.js, like that would be part of the system, not part of your application in this definition, right? Of course, it logically speaking, or actually speaking, it's part of the JavaScript process. The Node.js process is part of the JavaScript process, but here we are separating the two a little bit. Either way, both of them can generate data that we can then collect in and put it in some sort of data repository for dynamic analysis, where we can basically have some sort of database, dynamic analysis engine. We can just send some queries to the database that can use that data that it collected from the running program. And then we can use that data in order to help you while you're developing and while you're writing your code or while you're running your application. And on the front end, of course, it's very simple. Just visualize it, to make it visual, and then allow the user to interact with it in a meaningful way. And that is, I think, basic interactive debugging model. Oftentimes that will be integrated with your IDE, but it doesn't have to be. And then all of that needs to probably need access to the source code in order to help you map things back to lines of code. There's some examples of that. For example, the traditional debugger, it has that control module. It also has the basic dynamic analysis engine to help you determine where the breakpoints can be set on and so on. But and of course, it visualizes the values and the call stack, but it doesn't do much more than that. It's very limited in that. The profiler is maybe a better example. It collects quite a lot of data. So profiler, you run that and you determine where's your bottlenecks, why is your program running slow or slowly. And so it will trace the timestamps of all the function executions and uses those timestamps to render this flame graph or some sort of visualization of where the program spent how much time. And essentially it renders some sort of call graph. That's kind of like what it often does. And then you have a coverage reporter. It's kind of a similar thing. The coverage reporter, you run that on your test. So you run the test, and then the coverage reporter will determine, okay, which line of the test, which lines of the code were actually executed by what tests, and did you actually cover the entirety of your program? It's coverage reporter. So that's also one of those examples. By the way, the coverage reporter doesn't have too many interaction features, but it has some cool visualization features. And then Dbux, that's the tool we are talking about today. That, of course, we will see in a second how that works out. There's other types of innovations. They are rare, but they are certainly there. And for example, one thing I would like to always mention is Replay. They are doing a great job. They have these amazing collaborative debugging features. They also have backstepping, so you don't only step forward, you can also step backward. They're using some snapshot-based technology there. I think they only went live like just last year. So then they have been, I think, expanding quite rapidly. So they have been doing a great job. Another thing that the replay is doing is you run your tests and you can then integrate that replay with your CI. So you can not only you can debug in the cloud, where basically the debugging session is available not only to you but everyone else, and you can like debug together. But also, if your CI runs, the test fails, you get a button that basically sends you right there to the failing test and to the debugging session of that failing test. Amazing stuff, very useful. All right. So, but today I want to talk about more this dynamic analysis engine, the visualization, and these interaction features. But mostly, actually, I will demo how that works out, and that's it. There we go. And then, yeah. So today, Dbux is an omniscient debugger. That's what I want to introduce. An omniscient debugger means it's very slow. That's kind of what it means. You know, it's always pros and cons, but very slow is relative. So it takes a few seconds to run an application instead of just 0.1 second. It takes like 2 seconds or something. Most of the time, this is just fine. But other than that, you don't need to do anything else. You just need to run it once. It gets all the data out. Omniscient means it just knows everything, quote unquote. It doesn't know your grandma's birthday, but it certainly knows a lot of things about your program at the very least. And then it just arranges all of that in some visual UI and allows you to interact with it. And we will see how that works in a second. All right, we will skip over this part because, yeah, not today. And we will just jump right into one aspect of debugs, that is our new program dependency graph. So let's look at that. So this is where I'm getting very nervous because I'm going to do a live demo. This is just not a good idea, but I thought, why not? All right, let's do this. Maybe it works. All right, so far so good. I think nothing crashed quite yet. All right, great. So this is an example. So this is just some code. It's just some random test code. Don't put too much, well, you know, value to it. This is not very great code. It just illustrates a few very basic concepts. So that's what we want to do. We want to understand today, well, when we talk about algorithms, because this has many applications, and one of them is algorithms and data structures, and that's the one we want to focus on today. How do algorithms usually work? Usually, especially on these platforms where you can practice them, and in many types of other scenarios, it's a function, a singular function, has a few parameters and a return value. So the parameters are the inputs, the return value is all the outputs, and you basically have to write a program that somehow takes the inputs and converts them or puts them together in some way, shape, or form and creates some output, and that's it. So in general, the most basic kind of algorithms would look exactly like that. You have your inputs right here, right? You have A, again, the parameters are the inputs. A, so you can click that, actually it takes us right to the code over there, and B over here, the visualize that over there. And then we have a return value down here, and that's it. So A is 1, B is 2, and then this whole thing returns 442 for some reason. Why does it return 442? Well, because it does these additions and multiplications. And now this is just the overview. So the most basic overview always gives you a complete summarization of only how inputs and outputs are connected, and that's it. Now we can open this whole thing up and we can take a look at exactly how that came to be. And we can see, okay, well, okay, we still have A, B over here and B over here. And we have this total mess over here in the middle. Of course, it takes some getting used to. So why is it? So first of all, I want to address the elephant in the room, because this is going to be very difficult to follow just in general. Why is it difficult to follow? Because it's always difficult to follow any type of code, right? If I write the code, it's easy for me to follow, especially if I can take my own time. But if you try to follow someone else's code on their time, it's going to be very difficult to follow no matter what, because code is complicated. Our programs are complicated. I'm just trying to illustrate a few of these ideas here. So we're still going to do this, but keep in mind that this is, of course, best used when you use it on your own code, or sorry, at the very least at your own pace, so that you don't have to go by my way of thinking, which is not going to be sufficiently helpful to you, which is just always not, you're never going to be able to catch up with my kind of like way of thinking. So keep in mind that this is best used, of course, at your own pace. But nevertheless, so if you humor me for a second, we can maybe see a few cool things here anyway. So first of all, we see that the A and the 10 over here, so we see that over here was added together. Why? Because of this plus over here. I click that, it takes me to the code over there. Over here, it also shows me other information about this piece of code. For example, this value is, again, I click this, took me over there. The value of this A plus B is 11. It executed twice. The first time was 11. The second time was 442. We know all that right away. That's all basic debug features. You all see these weird decorations here. Also just part of debugs. It kind of illustrates you where the code executed. It gives you a little bit of a sense of that. And so this is the first thing. The next thing, what happened? We took this whole thing and put it in a variable called C. So we click that, it takes you over there. The value of that is 11, of course. And then we took this value of 11 and multiplied it with the value of D over there. So if I click there, again, that's here. And then D came in from there, right? So if I click here, so it's the C came in from there, and then D came up from there, and then we multiplied the whole thing together, the two things together, it's 440. And then ultimately we came down here, which is down here, sorry, the add over here, the return statement, that's 442, right? So this is added together in there, takes us to the return statement, and we return 442. Great. Just is this valuable, right? So it just gives you a basic sense of, okay, even such a simple piece of code, you're theoretically just, I don't know, maybe 10 lines of actual code, can be super, super complicated and very difficult to look at. One of the reasons is, of course, that you see more than 5 things on the screen at a time. Generally speaking, our short-term memory, I think, has been established. Like if you do 5 or 6 things at a time, you can like quickly recognize it and use your short-term memory to reason about it. If it's more than that, you need some technique in order to basically put together your mental models and put together these sort of like data structures in your brain to keep track of all these different things. That's why this is difficult to look at. So I will try my best to always keep it nice and easy. Like basically we're only going to look at like a few things, and we expand it. We only going to look at a few new things. That's what I'm going to try to do as we move along into the next sample. All right, next sample, let's see if we can do that. Okay, I'm going to go import it because I've got it prepared. So far so good. I'm going to go there. I'm going to select the thing. Again, another main function over here. It's very, very simple, as you can see. I'm going to see a visualization of that. All right, this is nice and easy. We're calling the main function here, array 1, 2, 3. Also, we give it a 4 and a 5, and we visualize the whole thing. And basically what we do here is we take the A, which is again 1, 2, 3, and push these 2 values into it, and then return a copy of that. And so we would see 1, 2, 3 pushed 4 and 5. So that's 1, 2, 3, 4, 5. That's kind of what we would expect. And it's exactly what we see. We see A over here, and we see an X over here, Y over there. And then all of that's pushed together into one array, and then everything is returned. You can see exactly, you can follow these lines, can see exactly where each value came from, where the last time it was written to. That's where it will point to. And that's how we will deal with arrays and objects. So basically any sort of dereferencing, any sort of nested data structure will be like that. And once you have that, you have these variables, you have your computes, right? So like plus and minus. And then you have these referenced data types, those 3 things. Then you have all of your data flow. The only thing that's missing is, of course, how it is being guided through your program. It's being guided by control flow, which is your ifs and your loops and your function calls. Of course, there's others. There's ternary expressions, and there's your certain logic operators. They're all inducing branches, but in the great scheme of things, you have your ifs and your loops and your function calls. These are the main things that are inducing control flow, which we will now look at in another example. All right, so this data flow. Let's look at some slightly more complicated example. All right, that's this. I just took that from the official JavaScript algorithms repository. I don't know if this is all that official, but it's this guy. They put it out there. It's like one of the most starred GitHub repositories out there. It's very strange. You would think it would be like Python algorithms. No, I think it's like currently number 15 in the world of all the stars of the history of GitHub. The JavaScript algorithms repository is number 15 right now. So this is one of them. It's called rain terraces. So let's look at this little algorithm. It's actually not too complicated. We look at a visualization of it. We're also going to see the graph over there. Okay, great. All right. All right, let's look at a visualization first. Here we go. All right, so this is rain terraces. Whatever. As you can see, I found a visualization that just maps exactly to what we have here. So we have 3, 0, 0, 2, 0, 4 as inputs. It's exactly the same. This is great. So when you do algorithms, one of the first things I would always recommend is find an existing visualization if it's, you know, a common algorithm that is already in existence. If you're trying to learn a completely new kind of algorithms, starting with those visualizations is always very helpful. But of course, it's very limited. Like the visualizations that these, the effect that these kinds of visualizations can have is very limited simply because this is the concept and it doesn't help you map the concept to the code. And that's kind of where our thing comes in. Here, we can also only have one input, while ours can work with any input. We can just run it again with any input. We can see the final visualization of that. But certainly, having said that, having these dedicated domain-specific visualizations can still be super helpful. Absolutely not against that. This is definitely not something we can replace. But what we can help you with is understand how all of that maps to the actual execution of your code. All right, so let's look at the algorithm. Sorry, got sidetracked there. The algorithm is basically, it gives you this array with walls inside of it. So every one of these numbers is a wall of that height. So wall 3 is here, and then there's a height 0 wall here, so no wall, and so on. And now what you want to do is you want to compute the area between all these walls that is not filled out by any individual piece of wall where water can be held, right? If you try to stack up water up here, that cannot be held because there's nothing to the left that will keep it in. So this is kind of how it works. You will have to find kind of like the highest on the left and the right, and then kind of see it go through the whole array one step at a time to determine how much it contributes to the final result. This will be your job. You will basically compute the final value, which is 10 here. All right. This is 3, then this is 3, and so on. If we look at this here real quick, let's open this up. So we can open up everything. All right. Oh, holy crap. This is just very complicated. Now, first thing we can do is we can go and make it nice and vertical. So we do that. And then it's a little bit easier to read because now it goes by order of execution, but it's actually it's a mess. Okay. So what we want to do is we now want to go back to the original and then do it one step at a time. So let's look up at only one level. Okay. Inside of it, we have one for loop right there. And this is a summarization of the for loop of all the data rights that are contributed by this for loop. And then we can open up this for loop and we'll see the individual iterations. So you can always go down like that. Basically, take these branch blocks and open them up or close them down one at a time. And so this is, I think, a very useful visualization. Now you can see exactly what each iteration of the for loop did and how much it contributed to the final result. So the final result is, again, is 10. Why? Because, well, the first step, well, actually, it's the second step. As you can see here, this is iteration number 1. Iteration number 0 did not contribute anything, so we don't see it. So in iteration number 1, we will take index number 1 and compute its contribution. And because of the guy on the left-hand side, the wall that is height 3, it will be 3. All right, and then we will go down to the next iteration. And as you can see, actually, if I click into it, we will see why it happens, because here is the water amounts being summed up. And there's 3 inputs. That is its previous amount. That is the next, basically the layer that currently caps it. So for example, here it's 0, this index 0, the 3. And then it's the current index's amount. So all of these 3 things contribute at every step. So this is why at every step you will see, except for the first one, you will see here 2, but here you will 3, 3, and 3 inputs. You will see these 3 edges coming in. Every one of them has exactly 3 edges. And this is summarizing an entire iteration of that loop. And yeah, so the first time we see that this 3 comes in, the second time we see that this 3 comes in, the first, the fourth time, or in iteration number 3, we see that only 1 got contributed. Why? Because if we follow this blue arrow, we can see, oh, this was value 2. So because there was only, it was value 2, so this only contributed 1 guy, and so on. All right. Again, this is very difficult to follow. And if you're not into algorithms, this is certainly very difficult, or not interesting to you. But if you are into algorithms, or if you want to understand how to make sense of more complex code, I hope this can be kind of helpful to you. I will go so far and actually do a few more examples here. Let's see here. Let's go a little bit crazier. So we will do the same algorithm one more time, but this time a little bit different, because as you can see, sorry, this time it was always capped by the left-hand side by the 3. So every one of them, you see that one of the arrows goes back to 3, because that was kind of like the controlling factor, because it just happens to be the controlling factor in every single step of this algorithm for this input. Now let's look at a slightly different input of the same algorithm. Okay, again, we select something in here, open the graph. All right. It's the wrong thing. Oh, yeah, right. Sorry, this was multiple things at once. So let's go down here. This was 10, 6, 4. Forgot which one it was. This is just great. All right, fantastic. Yeah, this looks pretty good. All right, cool. Yeah, this must be it. Yeah, I think so. Yeah, this is pretty good. All right. So this time the inputs are these. And as you can see right away, this guy again didn't contribute anything because that's the wall. It won't go, it cannot contribute to that. And this guy also did not contribute. And then if we open it up again, step by step, open one level and then open this up, you can see that iteration number 1 contributed, and iteration number 3 contributed, and iteration number 5 contributed. And then you can also see that, for example, iteration number 5, it contributed because of the right-hand side. And then for number 3, you can also see, sorry, let me do that again. For number 5, we can see that index number 5 is 1, and it was capped by the right-hand side guy. And then for iteration number 3, it was also capped by the right-hand side guy. And here it was capped by the left-hand side guy. It's kind of interesting. No, also the right-hand side guy. Anyway, so this is just one way of basically looking at not only the whole loop, but every iteration and see exactly the contributions of each iteration that it has on the whole algorithm. All right. All right, let's do let's try this. Okay, let's do one more. Maybe one more after that. Maybe one more after that. We will see how much time we will have until when 55. Oh, sorry, Jürgen, you said 45 minutes max, right? Or like 40 minutes?
Yeah, if we can wrap up in 5 minutes, that would be great, actually.
All right, no problem.
Okay.
All right, let me do one last little.
Sure.
Right here. All right, let's do this. All right, this is sorting, bubble sort. Okay, so let's look at bubble sort real quick. As you can see, this captured this bubble sort algorithm. Bubble sort, how does it work? It goes from the left to the right. It's the wrong version of the code, fine. It goes from the left to the right. I guess my video is not mirrored. I guess this is your left. I hope so. It goes from the left to the right and basically bubbles the biggest value up to the right at every iteration. So first the biggest, then the second biggest, and the third biggest, and so on. That's what bubble sort does. Let's look at what it does in detail. So this for loop does all the work. So that's why it looks kind of like iffy. I'm going to open it up. I'm going to look at the iterations. All right, and we can see the different iterations of this for loop. We can see that the first one's super complicated. Skip that. Look at the second one. The second one, it only did one swap. That's it. It just, the bubbling is, it swaps elements whenever it encounters something where, something needs to be bubbled up. Whenever it encounters an element that is bigger on the left than it is on the right, then it bubbles them. It swaps them. So this captures it right away. So you can see that the iteration number 1 is only doing one swap. And then iteration number 2 is doing only one swap. And iteration number 3, because it bubbles it all the way to the right, and then it basically bubbles it back down, or rather, that's kind of like the effect that it would have, that ultimately the smallest element gets swapped last. I guess that's what I meant. And then here you can see that there's only one swap in this iteration, and this is how the final value came to be. This is, I think it's fun. And then of course this one is a little bit more complicated. What happened here is that the 5 was bubbled all the way from here to here. So what you can see is that there's 3 inputs of the 3 and the 4 and the 2 that got moved to the left, and then the 5 got bubbled over to the right. And every one of those movements is captured with an arrow over here. All right. All right, this is it. This is kind of like sums it up. So I think, I probably already said way too much. And I think, most people might be falling asleep. But I hope this gives you an idea of a very different aspect of our algorithms and of our programs. And that these complexities that are happening, well, let's put it this way. If you're not aware of them, if you think that these complexities are not worth your effort, there's a good chance that you will struggle with anything, right? You will definitely ultimately always come across bugs and problems in your programming life. And you will ultimately have to build these mental models up. And if you don't already have the mental models while you're debugging, then your debugging process will probably be just very, very painful. So this is at least my own experience. Sorry, I didn't want to say that, okay, this is exactly how it will go for you, but this has been my experience. And I believe that this can help us establish our mental models. If we can at least, okay, this is actually way too complicated. Let's make this a little bit easier. Slightly better. There we go. So there we go. So there's like these individual bubbles, and you can see that, these are like the individual swaps that you can see there. If we can have some way of visualizing this, I believe this can be extremely helpful. Yeah. Well, that kind of sums it up. Sorry for not being super prepared today, but I hope someone had some fun. There you go, Jürgen. There you go.
No, honestly, this was fantastic. It was super cool, very practical. So I don't know what you mean. This seemed very prepared, actually.
All right, thank you.
Okay. No, this was really, really nice. Thank you so much for talking to us. I want to open the floor up for questions, maybe from the audience. Having seen this and maybe reflecting on your own debugging experience, are there any comments or questions you want to ask Dominic, or bring a discussion point into the group? Feel free to either put something in the chat or just unmute yourself.
I will also put the link for my survey in the chat. I mean, I don't know if people are so inclined to give me some feedback, but I like to do surveys after every talk. So
absolutely. We'll also put. Oh yeah, thanks for posting the link. We're also posted into the forum, so this is recorded. People will see it afterwards, and definitely please provide some feedback for Dominic. I think he's given us our time, his time, so let's give him time back also.
Thank you. Yeah. So, any questions? So, or anything? Any comments? Many thoughts? Nothing at all, or kind of like, oh yeah, I've seen that before, or this looks weird, or it's like it doesn't make a lot of sense.
I have a few points that I do want to discuss, but maybe if there's one or two beforehand, not so far. But if there is in the next couple of minutes, please do hand out. So one thing that you tackled hands-on, which is always a thing with large-scale visualizations, is as programs progress and become more complex, it becomes hard. I think you did a really good job of showing what we can do in terms of incrementally expanding these sorts of things to handle this problem. Because if you look at a lot of the literature on visualization for programs, especially in dynamic analysis, you have this explosion of the state space, and then it becomes another needle in the haystack kind of problem within your graph, right? Like you showed one option here of dealing with that by incrementally opening up these branches. What do you think are other options that you may have thought about or you've seen maybe in other debuggers?
Well, first of all, I don't think you see a lot of this kind of like multi-resolutional approach where you can kind of zoom in and zoom out of it in terms of the dynamic execution behavior of your programs. I think this is very, very rare. And thus far, yeah, I'm not sure. Right now, off of the top of my head, I think I've not seen anything like it. This is so few of these interactive debugging innovations that are happening. So in order to be able to kind of visualize things and kind of be able to zoom in on the thing that you really care about, or and then be able to zoom out again, or basically, or more importantly, maybe you zoom in on one thing, right? Let's say you're on one part of your code and you try to connect it back to that other part of your code, like way over there. I think that this is like, these are like the two main problems that I consider. Number one is what you said, that zooming in and out, hiding detail and or showing more. And then on the other hand, being able to connect it to all the meaningful places that it needs to be connected toward. And then being able to basically map the two on top of each other. This is like big open questions. And to be honest, right now, I don't think I have really thought of better solutions quite yet. This is obviously But it definitely has to do with importance sampling. So let's say you want to zoom in on something, you see a lot of detail. It gets very messy very fast. So what you might want to do instead is you want to zoom out all the way, but then you see important little things that are maybe relevant or extra relevant on the lowest level that are being highlighted. I think that is an very, very important step to take to be able to understand or even be able to assess how even on this big global, like zoomed out view, to see the most important things that are happening in your code at any point in time. I think this importance sampling is certainly one of the things I've been having my eye on. Yeah, I don't quite know how to do that quite yet.
It is certainly like active research, and as said earlier in your talk, there's not a lot of work in this, and it's not also very well received in the community. That brings me sort of to my next question. So there was some effort a couple of years ago in academia, especially, and now it's sort of bubbled up into industry with I don't know if you know Tudor Girba and the group that he had around in Bern, where
Sorry, can you say that again?
Tudor Girba, he was a researcher in Bern many years ago, and he looked into this concept called moldable debugging. I don't know if you've heard this term before.
No, I'll write it down for at the very least. Go ahead.
Okay, yeah. So moldable debugging is this idea that our debuggers or tools around navigating, understanding source code should not be static. That should not be this one visualization, but they should be moldable in the sense that you should be able to use these structures as data structures, and then be able to build your own visualizations on top of it by writing your own code, which is the philosophy that came out of Smalltalk and Faro, where everything in your IDE was scriptable. So I was wondering, I mean, since you don't know it, so just your ad hoc thoughts maybe on this sort of idea of being able to adapt these sorts of graphs that you're showing with your own custom script.
I remember one of the papers, like one of the most bigger influential papers, especially in Omniscient Debugging, is the Omniscient Debugger. Sorry, no, that's actually ODB, I think. ODB, so Omniscient Debugger, I think. So the Omniscient Debugger, TOD, is actually yet another one. So it's two different projects. So that one, the ODB, I believe that's one of the first times that I saw that, oh yeah, so they offer a query language. So you can actually write some queries into it. And I thought, well, I'm not sure if people are going to use that because people are lazy, right? We are very lazy, but much, much more importantly, those queries, they need to change all the time. We're just looking at that thing, need a different query than when we are looking at the other thing. And in fact, we're seeing that in our debuggers, in the traditional debugger. Most importantly, we have the watch lists. Watch lists are very, very rarely used, even though they can be very powerful. The problem is organizing that information in a meaningful way and allowing you to apply it in the right moment. So Moldable Debugger, it sounds exactly like they are trying to tackle that specific problem, to say, oh yeah, so I have that script over there and I can now easily apply that to this debugging scenario over here, and try to integrate it like that. But I have also not quite yet considered possibilities of how to make it actually really nice and scriptable. Aside from the fact that, of course, we have our engine of our dynamic analysis engine. Basically, I looked today, I think we have like 250 types of queries already in like 5,000 lines of code. This is just basically most fundamental queries. And then on top of that, we have all kinds of other things like indexes and then like all kinds of other data structures that are on top of that. And allowing you to basically just tap into that can be very useful. But that, on the other hand, requires you to understand the language of dynamic analysis. And I think that's where it gets tricky. So when you want to do your own plugins, of course, you can do some visualization, write some nice little visual plugin on top of that. But that's more like extension development. And that is actually very costly and takes a lot of time. So I'm not actually sure how often are those features used for Faro and Smalltalk? How do you think about that?
So I'm not personally in the Smalltalk Faro world, but the people who are very into it. So oh, yeah. I think they believe in this culture and of adapting your environment, which I think is
aspect-oriented development. Is that also part of that?
I think aspect-oriented development does not have to do with the tools itself, right? Which it's just injecting code within your existing code.
Right. But I remember that it very, very faintly that there were certainly some approaches to using these kinds of like tools that are aware of these aspects and help you and make it like pluggable. But yeah, it was not like about the tool development. It was just like some Eclipse plugin or something. So I guess it's very different there.
Yeah. No, but check out the community. I think they're very passionate about what they do, especially Tudor, which I think he was active in the scene like 10 years ago. So now he has his own company doing this kind of stuff. Definitely interesting. I think the company is called Feenk, like F-E-E-N-K. No, L-E-E. Yeah, Tudor Gierba.
Right.
He was a student of Oscar Mierstrass from Bern.
All right. Also probably like Smalltalk and Pharaoh. I mean, I've seen them before, but like I've never really paid a lot of attention to them, to be honest.
Yeah.
Right.
I think just Pharaoh.
Yeah. Oh yeah, probably typo.
Okay. Before I make my last point, just a last option. Any questions for Dominic? Any comments on the space of debugging? All right, so let me ask my last question then, which is, have you considered any option of sort of marrying together the source code, this blueprint, as you said before, which is totally correct, with these dynamic aspects? So this is a work that I've been doing in the performance world, like marrying profiling and production performance data within the IDE, within the source code, sort of combining this natural instinct of reading and building mental models with appending more data on top of it, right? This in situ kind of way of combining this.
Yes. Oh, absolutely. So Dbux is all about that, right? So if we look at this real quick, as you can see on the very basic, most fundamental level, you can click anything and it takes you there.
Right.
And then
you do have these overlays, right, in the code that you have these red
and then
stars,
we have a little bit of code augmentation. It's right. Very basic. It's not that much to look at, and it only really serves the purpose of kind of seeing very basic concepts. This is kind of like misplaced because this is actually a different version of the code than what I ran it on. Doesn't matter too much. Either way, there is some things that it can do for you, but it's very limited. So I also believe that to have that is great. For example, just basic things like the Git thing, when you the Git blame, the inline blame thing, and so on. And then, of course, your test runner extension, you have a little button on top of your tests, and you do that. I think this is amazing. But yeah, currently we have also like not considered better code augmentation. It's also a route super interesting, haven't done enough of yet. Certainly, currently working on this is just taking up all the time, sadly.
No, absolutely. I know. Honestly, amazing tool. When you said you just developed it like 6 weeks ago, like started, that's insane.
It must have been like I don't know, like I've barely been sleeping, but it must have been some 5,000 lines of code now thus far.
No, it looks amazing, honestly. So amazing effort, really cool. Quick ad for code augmentation. I had 2 bachelor students that are currently finishing up their thesis, who worked on a framework for code augmentations. So sort of a domain-specific language where you can define where do you want to have these augmentations and what the behavior is. I'd be happy to send something to you.
Right, sure, absolutely. Yeah, just send it to me. It's even easier. Yeah, right.
Exactly. Cool. And maybe the other ad for the people around here, and then looking at the video, Dominic and I have been talking about maybe working together on some of these things, because there is joint interest in improving developer tooling. So if any of you are interested in a bachelor thesis or a project of some kind, please do reach out to us, and we have ideas of how we can improve this tool, ideas about new tools, and yeah, we'd be happy to work together with students who want to work on a thesis.
I think I'm not sure if that's true, but Python Tutor, I think one of the reasons why it just really got so big, or like why some of these are getting so big, is because it's just online in the browser. So you just open the browser and you can click into a sample or paste the code in there and you see the visualization right in there. All of this is JavaScript. All of this is really easy to port to the browser. Most of it actually, like, for example, this whole visualization is just entirely a web view. So a lot of this is already about, so porting it to the browser, I think this would be really super useful. Then you just open it, And so this would be, I think, a very interesting project. Not that complicated because you don't have to actually go into that many aspects of dynamic analysis to actually contribute. It's one thing you could do as an example. Or of course, anything else. If you are really interested in debugging or dynamic analysis, of course, there's a billion things you could do there as well. But I think most importantly, if you want to aim for impact, I think, yeah, put this in the browser. I think it's going to be tons of people who would be interested.
Yeah, and obviously, maybe not obviously, but I want to make it obvious now. All this is open source, so you will be contributing to an open source project. You know, you can send it around, brag about it. So I think that's also a really cool aspect of this.
So that's always a possibility.
Yeah. So in that case, I think we're out of time now. Thank you everyone who joined in live, and I will be posting the recording in the next 1 or 2 days. Thank you, Dominic, so much for your time. Thank you for this really cool presentation and demonstration. And yeah, have a wonderful rest of the week, everyone.
Thank you. Have a good week. Bye.